So I want to make some change here. This is proposition 1.4.5. Proposition 1.4.5, and let X be a non-empty set. Then there are two parts, that if that is, if phi belongs to Px, then phi inverse belongs to Px, implies or implies phi is 1 1. If phi belongs to tau x, then phi inverse belongs to tau x if and only if phi is 1 1 and on 2. So see, we have to prove phi inverse belongs to tau x if and only if phi is 1 1 and on 2. If phi inverse belongs to tau x, of course phi inverse goes in Px, and when phi inverse goes in Px, we have already proved by part that phi is 1 1. So what is remaining to prove? Remaining is to prove is that phi inverse, if phi inverse belongs to tau x, of course it implies domain of phi inverse is equal to x by definition, correct? So domain of phi inverse is x, it means image of phi is x, because domain of phi inverse is equal to image of phi. So image of phi is x, it implies phi is onto. So in this way both parts are proved. So we move forward. Now we start next definition. A relation rho on set X is called equivalence relation. If rho is reflexive. What is the meaning of reflexive? That is, you can say that 1x is contained in rho, correct? 1x means, what is 1x? Or you can say x, rho x for every x belongs to x. Both are same. This is the equivalent definition, x rho x for every x belongs to x, or 1x. 1x is what? Well, everybody knows that x comma x belongs to x cross x, such that x belongs to x. Second is what? Rho is symmetric. That is, rho is equal to rho inverse, or you can say that x rho y implies y rho x for every x y belongs to x. Correct? If x comma y belongs to rho, then it implies y comma x belongs to rho. If y comma x belongs to rho, it implies x comma y belongs to rho. So you can just also write rho equal to rho inverse. Third, rho is transitive. That is, rho composition rho inverse is rho composition rho is rho. or you say that x row y and y row z implies x row z for every x, y, z belongs to x. Means what is this? X row y means when x comma y belongs to row and y comma z belongs to row, it implies that x comma z belongs to row, like this. So this is equivalent to this. You can take element here and you can show that it goes here. And converse part is trivial. Of course, row is a subset of row composition row. No problem. So row composition row is equal to row. This is transitivity. Row equal to row inverse is symmetricity. And 1x is contained in row. This is reflexivity. Is it clear? So this is the example of. This is the definition of equivalence relation. Now one remark is there. If rho is equivalence relation on set X, then domain row is equal to X as well as image row. So how we prove that? If row is equivalence relation on set X, all of you know what is domain row, isn't it? So try to prove that domain row is equal to X and image row is equal to X. See, when it is given, since row is equivalence, therefore 1x is contained in row or not? Is it clear? So it implies that domain of 1x is contained in domain of row. And what is domain of 1x? 1x is what? 1x is set of all x comma x. X belongs to x. So domain x is what? It is whole x. So x is contained in domain row. And of course, domain row is contained in x. So in this way, x and domain row both become equal to each other. In a similar way, you can prove that image of 1x is contained in image row. You can prove. So next definition. A family phi is equal to ai, where I belongs to I of subsets of x, of subsets of a set X is said to form a partition of X. If Number one, AI is non-empty for every I belongs to I. Second, that either AI intersection AJ is empty or AI is equal to AJ. For every IJ belongs to I. Third is X is the union of AI, I belongs to I. So see, this is the family of subsets of X, and we say that this family forms a partition of X, isn't it? Partition means that for example, this is X, correct? Now the situation is like this. This is A1, this is A2, this is A3, this is, you say, AI, like this. So in this way, these subsets of X forms whole partition. Partition means that every subset of X is non-empty, correct? Number one thing, every subset of X is non-empty. Second thing, either any two subsets are disjoint or they just overlap to each other. They are equal to each other. It is not like that some elements are common in two subsets of X. No. If they form partition, so these two cases, either there is no intersection, they are disjoint. For example, here A1 and A2 are disjoint, or you for example, it is like that A3 is equal to A4 here. A3 is equal to A4, for example, like this. Third, that all, if you take disjoint union, isn't it? Then you see that it will cover whole X. X will be the union of this. So this is the example. This is the definition of partition. Now we will do proposition 1.4.6, and also we will do examples, because you see mathematics is that in mathematics there are three things: definition, example, and related results, correct? First we will see proposition 1.4.6, page number 20. Let rho be equivalence on set X. Then the family phi rho is equal to X rho such that X belongs to X. Of subsets of X is a partition of X. Is a partition of X. First, I will prove this fact. First, I will prove this. There are also some parts more, but first I will prove this. You see the proof. See, this is you have to prove that this set is a partition of X, correct? This family is you have to prove that it is a partition of S. Since rho is equivalence on X, therefore x belongs to x row. You see here for every x belongs to x. So x row is non-empty. I mean to say that to prove any subsets of x family, any family partition of x, what you have to prove? You have to prove three things. That is, you have to prove that every subset is what? Non-empty. Every AI is non-empty. And after that, if you proved, you have to prove that either AIE and AJ are disjoint or both are equal to each other. And third, finally, you have to prove that X is the disjoint union of all AIs. Here, AI is what? X row. So you see, since rho is the equivalence relation on X, so of course rho is reflexive. So X belongs to X row. For every X belongs to X, correct? So X row is non-empty. For every X belongs to X. First thing. Second, if you assume let X row intersection Y row is non-empty. So we show that X row is equal to Y row. This we have to show, correct? Because if they are empty, if intersection is if they are disjoint, no problem. But if there is element common, then both must be equal to each other. This we have to prove. So X row intersection Y row non-empty, it implies what? There exists some, you say Z belongs to X such that Z belongs to X row as well as Z belongs to Y row. It implies that X comma Z belongs to row and Y comma Z belongs to row. This we have. Now what you have to prove? You have to prove X row is equal to Y. You take element here and show that it goes here. Then X row will be subset of Y row in this case. So take any Z dash belongs to X row, for example. Okay, you just take any T belongs to X row. Then X comma T belongs to row. Correct? X comma T belongs to row. And now you see that it implies that you say that T comma X belongs to row. Since row is what? Symmetric. Better you write here reflexive relation. Reflexive on X. So T comma X belongs to row. So T comma X belongs to row and X comma Z belongs to row. It implies what? See, we have X comma Z belongs to row from here. So T comma X, X comma Z, it implies that by transitivity, it implies that since row is what? Transitive. So T comma Z belongs to row. So T comma Z belongs to row and also Z comma Y belongs to row since row is what? Symmetric. So it implies what? T comma Z belongs to row and Z comma Y belongs to row. It implies that T comma Y belongs to row since row is transitive. Is it clear? It implies that Y comma T belongs to row since row is symmetric. So it implies that T belongs to Y row. So we have taken element in X row and we have shown that it goes in Y row. It means what? It implies that X row is contained in Y row. Similarly, we can show that, you just write, similarly, Y row is contained in X row. So X row is equal to Y row. So we have shown that if for any xy, you see, for some x comma y belongs to x here. For any x comma y, you see, if this happens, x row intersection y row non-empty, isn't it? So what we have seen? We have seen that x row is equal to y row. In this way, this part is proved. Now, what we have to prove? Now we show that x is equal to union of x. Correct? Because here obviously x row is the subset of x. For every x belongs to x, isn't it? It implies what? Union of x row, x belongs to x is a subset of x. Now you take any y belongs to x, then of course y belongs to x row. For some x belongs to x. Of course, it is contained in union of x row where x belongs to x. Yeah, you just write, take any y, if you have taken y belongs to x, y goes where? Y goes in y row. And of course, y row is contained in the subset of union of x belongs to x, x row. Isn't it? Because it covers all. So y row is the subset of union of this. So it implies that x is a subset of union of x row. So x is equal to union of x row where x belongs to x.